let's start. Hope you had a great lunch. Great lunch. So now we're going to talk about the architectural patterns. More than for Windows Azure is architectural patterns for highly distributed, scalable systems, independent of where they are. Okay. So my name is Nuno Godinho, and as a disclaimer, this is my opinions and my opinions only. Okay, doesn't represent my company. Who am I? I'm the GM for software engineering and software CTO for GE Healthcare in Europe. So everything that is doing software in Europe is handled by me, and then I'm also leading the technical product management for the cloud, so cloud strategy for GE Healthcare globally. So also Windows Azure MVP since the early beginning of the program, 8 years now MVP, and then Service Bus champ. Anybody knows Service Bus? Pretty cool. You should take a look. If you need a service bus, the bus system is pretty good. So, as an intro to where do I work, anybody knows what this is? This is some of the things we do on a day-to-day basis. Software solutions in order to show this. So this is actually 2 embryos, and this comes directly from the equipment, from the Echo equipment, all in metadata, and we're generating slices and everything, and we generate the things in real time, and we're actually seeing the ones that run on the device as well as the ones that you can see on your laptop through the cloud, whatever. So this is one. Another one, you probably have seen this one. This is the new 4D Echo. Apparently, dads love it. I'm one of them.
It's kind of Halloween.
What?
It's kind of
Yeah. And one other one is, why is this playing? Okay. So this is another one. So there are several divisions. One of the things is this is with a microscope, but it's actually through software then renderized, and all the information that is here. One of the things that we're doing is all the changes on the cell split. This is a cell being split in real time, and we're getting all the tracking information and actually understanding if that's because the way to identify cancer is the way the cells actually break. This is actually cancer analysis. So the way the cells break, and this is in detail. This is actually a cancer itself, even before you figure out if it's cancer. This is part of the solution. So what we're doing is a lot of in real time getting the status. I did a talk on IoT. This is everything, all that status information is getting fed, then we're processing it, visualizing, but also helping produce the right drug into treating even before it gets a problem. So this is some of the things that that we're doing. Now to the real thing. It's very important when we're doing some of these things. It's very important the scale, understand the scale, and one of the questions was, can we leverage the cloud? How can we leverage the cloud? And that's been one of the difficult elements. So one of the things this talk is about is, what are the design concepts of designing to the cloud? Is it really different, and what do we need to think? Let's break it down. Then it's about what are the critical decisions we need to take when designing for the cloud. Any of you been working on microservices? Yeah? Okay. So microservices, CQRS, event sourcing, how can that come to the rescue and help with leveraging the cloud and leveraging Azure in order to make it better? Then some real life, so this is a real life highly scalable architecture in Azure. which started as a solution, normal service-oriented solution, which in order to support tablets, in order to run, costed about $2 million a year of Azure. Microsoft, for some reason, loved it. We didn't, because we were paying for it. And by using Microservices CQRS, we have much more customers being served with about $100,000 a year. And we serve more customers now than we served before. And we minimized the complexity and actually created reliability. And this is to talk about that and some of the lessons learned. So the design concepts for the cloud. When you say designing for the cloud doesn't mean really anything. It's designing for multi-tenant distributed systems. It's designing for multi-tenant distributed system with an abstraction on commodity hardware, internet scale, composed of multiple services. That's what designing for the cloud. We're designing in the distributed environment, running on commodity hardware, having the scale of the internet, and composed of multiple services. That's an actual design for the cloud. So let's start break it down. Multi-tenant. It's a multi-tenant distributed system. That's the first thing, is you need to understand that when you're designing something, you're not the only tenant in that thing. If it's a cloud provider, you won't be the single tenant in that cluster, in that hardware. You're not. You're going to be sharing with someone else. That means you need to, as normally you do, you need to understand how you're behaving and how behaviors from others potentially affect you. Things like in Azure, we have the throttling mechanisms. So I have limits on the number of operations I can do in a storage account. I have a maximum number that I can do. I have about 20,000 IOPS that I can do in a storage account. That doesn't mean that if I create a disk inside a storage account, I have 20,000 IOPS. Because that's limited. Because a drive, a VHD is different, works differently, it's a lot more processing, and then for that, I'll have the premium storage in order to get those types of IOPS. Okay, so I need to think I'm not the only one. So when I do the design, I need to design in order to track what's happening. I tried to connect to the storage account didn't reply, the storage account took 10 milliseconds, good, took 30 seconds, we have probably an issue there. If this continues, I might need to actually fall back to some other because there seems to be a brownout. Because one of the things in the cloud is outages are very simple to track, right? The only thing we need is we tried to go there, it's not there, it's an outage. A brownout is much worse because it's very difficult to track and it's actually affects us and we sometimes don't even see it. So a brownout is when the performance degrades so much that I actually get impacts on my application. For example, if I go from a millisecond to 30 seconds in order to connect to a storage account, while it's happening, I'm probably being throttled. Why? Maybe I'm hitting too much the storage account. If I'm in event hubs, for example, maybe I'm sending too many messages into the account and I'm going over the threshold. So I need to understand I'm not alone. I need to behave and others need to behave too. There is capabilities in the cloud, in Azure, that allow you to play nice with others, but you still need to think about those things, track them. The other part is distributed system. Yes, cloud solutions are distributed systems. They are distributed across multiple different nodes. For example, Azure has storage accounts that are in storage nodes. They have compute nodes. They have then, and those are our storage and our compute nodes for websites, for cloud services, for VMs, and so on. But then they have a whole range of other services which you don't consume directly the machine, but actually the service, like service bus, like media services. All of them are distributed systems. So we need to understand that latency is important. We need to understand how is latency going to play. So for example, we're now working on an imaging solution, and we need to understand the machines are sending the images. We need to go and process the image and do a lot of rendering and creating 3D models and so on. But the images are in multiple different locations. We need to understand even how we split with microservices, how is that increasing the latency? Because if it increases too much, it's unusable. If you have a too bulky application, it's a problem. Does that make sense? The other is an abstraction, running on an abstraction. Abstraction is important when we design for the cloud for two reasons. One is we're not running on physical hardware. It's virtualized hardware. It's virtualized systems that we are running. So it's not the actual thing, which has some impacts. But also, we need to understand which abstraction am I working on. Infrastructure as a service, platform as a service. Oh, it's platform as a service, but it's what type? Websites, web roles, worker roles. So I need to understand which abstraction I'm using, and then I should also abstract myself, as a good design pattern, is abstract myself from the SDK that is underneath. So one of the best practices when we think about designing for cloud is always using an abstraction layer, or using something like a repository pattern if I'm using for connecting to databases, always using dependency injection in order to make sure that we can actually change our implementation. Or go down the microservices route. And in that case, that becomes much simpler. So how do you eat an elephant? Small chunks. That's the concept of microservices. So commodity hardware at internet to scale. So we are going to have commodity hardware. It's not, one of the things is we tend to think, oh, doesn't matter. I can do this. I'll just get a bigger machine. Bigger machines cost money. And there is a very interesting thing now is a good and a bad developer are now not only seen by the code they write, but actually how much does it cost the code they write. So it's important to understand that I need to split things in small bites, because it's better to have a lot of small instances running together, because it allows me to scale up and down quicker and in a more cost-effective way than have big bulks of applications. That's why, again, microservices come into the picture. Then also, composed by multiple services. Multiple services, it's a combination. So when we work in the cloud, in Azure, for example, I build an application. For example, I need to manage a POS system. I'm building a POS system. So what do I need to do? I need to have a data store where I'm storing all the information, all the data that I'm retrieving. That's one service. It's a database service. And I can actually have multiple, because some parts is relational, some other parts are not, are time series and things like that. And some are document, because I have the pamphlets from the services or products that I serve. So those will be every single one of them, even if they are in the data layer, they are all different services. Then we have multiple services. Oh, I need a queuing system. It's service bus, either queues or topics or event hubs. One service. Then, oh, I need a worker that is picking up something. Another service. And suddenly we're already have 5, 6 different services with interconnections in between. So an application in this world is actually a composition of multiple services, which again aligns very well with microservices, what microservices is. So the critical design considerations when we move into the cloud, what would you say it would be something critical for us to think? How many of you have worked and developed for the cloud? Azure or any other? Started. What are the critical things you've learned so far? Do's or don'ts, doesn't matter. Everything's an opportunity. When we screw it up, is an opportunity to understand what not to do next time. One of the things is fat finger is an issue, is the capability of self-provisioning sometimes bites you. It bite me, I learned the hard way. So I left a couple of things running from one of the demos, and I discovered in my credit card that it was a bad idea. So yeah, having governance around whatever you create, it's really, really a good thing. Because you can have like notifications and things like that in order to say, hey, you're spending this much per day. Maybe this is a bad idea. If I had received that, I wouldn't get that thing. And by the way, I was playing around with a dupe. It was like 1,500 quid that I received. It's like, holy crap. So services at internet to scale, we need to consider failure is expected, latency is a fact of life. There is the light to speed and the speed of light and all of that. Consistency, upgrades without downtime. We need to consider that you need to understand what to measure, how you're going to operate. We would basically design this with a couple of things, like failure, design for availability. I need to think, how do I put in my application a possibility of recovering quickly and responsibly? For example, in Azure, one of the things in Azure and in any cloud, one of the things that we know, it's certain, is eventually something will fail. That's the only constant we know. When? We don't know. Which one? We don't know. But it will fail. The cloud didn't solve all the problems of hardware in the world. They just get the whole bulk of them. They gave them each node the ability to send information, and they have an artificial intelligence, a brain, which goes and say, oh, this is misbehaving, I consider that as down, and I move something to someone else. There is downtime in that, because I need to change from one to the other. Still, there is. But we need to understand, how do we design in order to get this availability? So one thing is, imagine you're having a service bus queue, and you have a worker role which is taking something from the queue. And yes, when it fails, the message is it's in a queue, it's reliable. So another worker is going to pick it up and continue. Will it continue or restart from scratch? Normally, what we have is, the implementation we do is, this is what we do. We pick up the message, and we do this, this, and that, and then we complete. We completely forget if the damn thing fails, what happens? How do we recover from this? Do we continue from where we left off? Can we actually build this? Did we implement idempotency right from the start or not? We also need to, in order to get availability, we need to understand what do we need in order to create the telemetry. More than logging is the telemetry. What is happening on my service right now in order for me to track his availability? Because sometimes what Azure provides you is machine is up or down. The service you're connecting is up and down. It's not saying your service is down. For that, actually, there is Now, have you seen the new portal? The new portal.azure.com? It's pretty cool. Now when you create something, you have a new service attached in a resource group, which is the application insights. That is the service that will provide you health in your application. But again, in the infrastructure which is running your application on, not your specific code. For that, you need to create hooks into it. But it's closer than before. Before, it's only saying this machine is either up or down. Now, with application insights, I can actually see application is down, but the IIS is not working correctly, or the main .NET is not working. I have this events and problems. And then if I want, I can plug in my own and use things like the same way as New Relic, basically ingesting my own stuff. But I need to think about that. Another part is building for scale. Scalability, you have scalability in mind. We need to understand what is the scaling units that we have. How do we figure out what the scaling unit is in a system? Imagine I have a UI. I have a UI which is a front end for some commerce. Then I have, and that is only the UI. It's the queries are all predefined, so it only connects and says, hey, here's the response. They already have the responses all together because it's already in cache. So, and in the other side, there is, whenever an order is placed, we're embracing eventually consistency, so we drop a message into queue with saying, this is what I have in my shopping basket, please do this order. It goes through the ordering worker role, picks it up, starts to process the thing, puts it into the database, and so on. When you think about scalability, scaling units are not individual services normally. Because if I scale the number of workers a lot, I might actually be choking the queue, because now I have too many things trying to connect to the queue at the same time, and I'm choking the system there. So, or if I'm increasing the number of worker roles and all of them are trying to write in the same database at the same time, what did I create? A concurrency problem. So I need to understand, okay, if I scale up this worker role, what other things do I need to scale at the same time in order for this to continue to work? And how does it behave? Is it linear scalability? Is it basically I'm going to have steps? This is scalability testing. So we will need to go through scalability testing. Let me scale this up. And then we see how the trend goes. And see, oh, I'm seeing a choke in this part of the system. So the scalability unit, the scale unit is actually these two systems together. And this is a challenge. It's a massive challenge. One of the things that will help you do this is, again, with microservices and CQRS. Why? Because you basically are decoupling all the elements in several different specialized units. And so you can actually spin up and down only that, because you're thinking about not the functionality, not when you develop a software, you're not thinking about the service itself. You're basically creating the service based on the business context. So it has all the steps. So you can up and down, scale up and down all the system. Also, the other part is data. So one of the things in data is you need to remember to have one thing, which is, what do you prefer? So you were in a SQL workshop yesterday. What's better for SQL? A lot of small requests basically every single service goes and does these own requests, or we just bulk a bunch of things, open a request and say, here it is, and then process it. What's best? Chatty or chunky? What do you think in the cloud? Chatty?
I got chatty.
Chatty has one issue when you go in the cloud, is if I have a lot of systems chatting very small things but chatting a lot, I'm actually going to hit the throttling limits pretty quickly. So for example, storage, if I go for SQL database, I'm going to have multiple servers, multiple worker roles. They are doing a bunch of calculations, and then all of them are putting something into the database. If every single one of them, so imagine they have like four or five steps, and they go and say, okay, in this step, update this table. That step, update second table. And they do this as a chatty type of application. What you're doing is that when you scale this up, you now have each of the worker roles times 6 are the number of connections that you open. Now you're not behaving correctly. You're destroying the scalability targets of that. So it's always better to chunk things and say, okay, I'm going to do this chunk of things, and the same thing when I'm taking messages from service bus queue or storage queues. I shouldn't take one message at a time. I should take a chunk. Why a chunk? Because if I take a chunk like 10 or 100, it will depend. Again, it's based on testing. It will depend what's the most successful one. Normally, it's around 10 is a good number to start. Then there are some systems, because the message is so small, that you can pick up like 100. Oh, but if you take 100, what happens then if it fails in the middle? If it fails in the middle, they all go there, which means that when you start, the first thing you need to do is actually start tracking what you do with the messages. So for example, even if it's a big message and you have to go through a bunch of steps, you should have a tracking mechanism, a correlation ID, in order to go and say, hey, message X, I started doing this process, I finished doing this part, I started doing this. So if it fails in the middle, I can pick up the same message. The guy goes and say, where were you? I was in this step 3, and I continue from step 4, 5, 6, 7. Right? I can restart from wherever I left off. This means that now, instead of having like 100 requests to the storage, to the service bus, I make one request, I get all the message at once. Normally, best practice is to use 1K messages. Don't go over that. If it's more than that, you should put whatever thing is bigger on the storage account, and on the message itself in service bus, you should put just the URL to where the other thing is. Because service bus is not, a message queuing system is not built for big messages. Small, fast messages, the bigger you put, it's not a linear scale, it's a crashing scale. Because if you go like, I had seen things like, oh, we actually put the dump files in the queue because we want to make sure that they are reliable. Yes, they are reliable. The problem is that they kill the messaging. So you lost the reliability there also. So you need to be very careful that. Also, the other part, so you need to think from the data perspective, what are you going in and how are you going to access the data? Agility. You need to think about agility. So, agile world, putting the agile practices, lean. So there is, I don't know if you read the Lean Startup. It's a very good book. Lean engineering, lean startup, agile, safe, things like that. It's great ways. It's about you going and trying something, failing fast. You need to try and fail fast because you need to adjust. You need to pivot around. You need to change something in order to make sure that you have the right thing. So you need to understand how to put that agility. This means, in for example, the cloud, continuous delivery. Not only continuous integration, but continuous delivery. In a cloud solution, you need to design things so that I can do continuous delivery. Every single time. So for example, if I think about Salesforce.com or for example, CRM Online from Microsoft, every single day there is an update. Every single day. It's not a major, but every single time they go, they check in something, goes to the process, continuous integration, all the tests automatically gets updated until gets to the deployment and they actually deploy, continuous deploy. Also, you need to make sure that when you're designing something, you create the governance around actually making sure that whatever people develop, they test things in the actual cloud. I know there's great emulators. Azure has the Express, the emulator Express. Really amazing. There is nothing that replaces the actual thing. So as an example, we had a whole team doing, before I was in services, we had a whole team doing a system for a customer. And everything was going well in the emulator. When we put it in the cloud, we actually hit what? Throttling issues. Of course, we couldn't test throttling issues in the local machines. So it's need to run in the cloud. You need to create agility, continuous delivery, continuous deployment, and you need to test the things. Sustainability. So sustainability, I need to make sure that whatever I design, for example, when I'm going to put service bus, worker roles, a web role on top of all these things to make the UI, I need to make sure that this system is sustainable. So I need to understand if the cost of running this thing is sustainable. If the monitoring, so one of the systems I had a customer before was really hilarious. They wanted something that Splunk does. They want to have the logging information, and Splunk does that really well. They look at the price of Splunk and they said, oh, this is too much. I'm going to do my own. Can you please do a logging system for us? I said, okay. Are you sure you want that? Yeah. And I said right from the start, I think it's a bad idea. It's not sustainable for your business. And they said, oh, it is. So because they have a calculation which said, oh, this is the number of compute nodes that I need, and it's much cheaper. Yes, but you're not doing, they have like 200,000 machines or something, and every machine was sending status logs, 5 or 6 different logs they wanted to get every 5 seconds. So now imagine this. And now imagine this being done the way they implemented was chatty. So every time there was an operation, that was about 2 or 3 trillion operations per month. And in storage, you pay per storage and per operation. That meant that it was about $2 billion just in operation costs to support that system. Was that sustainable? Yeah, Splunk really seemed very cheap at that time. So one of the recommendations is think about how much is that thing going to cost if it's sustainable. What type of insights are you going to put? So in Azure you have the store, you have application insights, really good. That provides you to get insights about the infrastructure, about the application, and you can hook your own. You need to think, so forget about logging. You need to think in the cloud, you need to think about telemetry. How many of you like Formula One or motorsports? Yeah. So they don't use logging. Logging means I'm only looking at something after they crashed, which is very not interesting. And also, I can change, like they do now, I can change the angles of the wings while the actual race is happening. Because for that, I would need to have telemetry, real-time telemetry, saying this is what's happening in the car, this is what the speed that I'm going, this is what the patterns that I'm seeing, and then changing real time. This is what you need to put in your applications. So an easy way to do this is with application insights. It allows you to do that. You also can use Elasticsearch, Solar, and things like that, where you actually store chunks and you use a little bit of the IoT mindset, and logging is no more than a status information. This is, so for example, the service, imagine that you have a system which is I'm uploading a firmware update. So what I'm doing is saying, I uploaded a firmware update, so let me actually put a message. Every time that is done, I'm going to put an execution status, say, I did this, and those were the characteristics. And this is important for two things. One is, I can then track how much time that took. I can also track how many of those happen, because that can generate me a business KPI, which is important also. I can actually track, if there is a problem, I can actually track where the problem happened. So this is an important part. And then for failure, and we already talked about it. Questions so far? Is this helpful?
The insight stuff.
Yeah.
If you're trying to hook it into your own application, does your own application have to be written in .NET?
For now, yes. They have Java SDK, which is getting better. If you have Java right now, New Relic. It's a better choice. So now microservices, CQRS, and event sourcing to the rescue. Everybody knows all of this. CQRS, common query responsibility segregation. Event sourcing, another design pattern. And microservices. So CQRS, in a nutshell, command query responsibility segregation is only about one thing. In a nutshell. There's some others, but mostly it's about two things. Is separating the way we query things and the way we operate things. So operations, queries. That's what CQRS is all about. So basically, instead of having here, we have a single system, we go through, and the UI gets a request, and then does something to the database, and then has a query, and goes to the database, checks whatever is in there, and sends it. That's very, if you want to scale, that's not going to scale too well. Why? Because you're putting the pressure here. And this, in order to scale databases, it's pretty damn hard. So what we have is we completely segregate this. So we have, if it's a command, if it's a user sending, please ingest something into your system, I have a service. The service goes, sends a command through a queue to a message bus. That goes, does whatever, the validations and whatever, and stores into the data store. Then, in the query model side, there is a worker that is normally called denormalizer or projection, which basically, if I'm going to show something to the customer, if I have that on my UI, there is one thing I know, is how is the customer, what type of information is the customer going to need, right? Because if I have a UI, we need to understand what are we going to show in that UI. It's a list of products, it's a list of something. Then we can have some customizations, but it's a list of products. We know what list is. So imagine that I'm inserting a product, went through the process, the commanding part, and stored the product. Didn't do anything about the querying. Now, as soon as this went, and since this is event-driven, as soon as it actually received the command to insert something, and then I drop a message saying the insertion successful, there is a denormalizer or a projection here that picks up that message, goes into the database, picks it up, generates the response, and so when the UI comes in and requests for something, you already have the response pre-prepared. If we think about this, that's what we do when we actually put, for example, caching in the system. That's what's happening. Caching is we go, we get the first time the response, then we cache the response. It's one of the parts. It starts with some of that evolved. This evolved from there. Okay? So, and I'll show in another example, CQRS. The other one is event sourcing. Event sourcing is about, I have a command. So in CQRS, I start with a command. Command leads everything. Command goes to a command handler. So CQRS has microservices, so it has complete segregation. A command is normally a message into a queue that says, for example, seat reservation, and inside it has 2 attendees for conference 157, for example. Then this gets by a specialized command handler, which is the seat reservation command handler. Only takes care of that, doesn't care about anything else that goes into that queue. He picks it up, goes and has its own logic in order to make the reservation for the 2 seats. It's a domain model, domain-driven design. So we then go and we see the seat availability, we aggregate all those things. We are constantly putting all the elements here, all the elements in the message. So the command handler dropped something to the message, then my service went, picked it up, and then did whatever it had to do and continued to place messages. Event sourcing is about storing the messages that are going through the bus in the order they are coming up. Why is this important? One of the things that some companies require is we require to have things like auditing. I need to understand, a company can come and say, I need to understand why are we at the right status, at the current status. Why is data like it is right now? What made the data look like it? If we actually store all the events, we actually have a single source of truth. Why? Because I can put every command back in the queue and I'll get exactly the same result. Exactly the same result. So I have repeatability. I have reliability on my system when I do this. That's the whole point of event sourcing. Does that make sense for you? So event sourcing is about storing the events in the right order which they happen. And then one of the things that we can do with CQRS is we can have a replay events. Because everything is a command handler and so on, I can put all the commands back in and they will replay everything again. And we'll have the exact same end result. For example, if I create suddenly in an incremental development, I go and create a new view in my UI. The only thing I need to put is, I need to put a new projection in my system and replay again my events. And I will get my execution events. And I'll get exactly the right visualization, the right results immediately done. So I'm pre-making the responses. So this is event sourcing. Then microservices. Microservices is a little bit of what CQRS uses in order to have, and microservice is more than architectural style because it actually changes the way you organize your teams and everything. So microservice, mostly in an architectural style, where approach is developed simple application. So one of the things, and Martin Fowler talks a lot about this, and it's very, very good. One of the things is they are very nimble, very small services. So you break the services down to a very small level. They are independent, they are lightweight, and there is nothing in the middle doing integration because they don't need it. The only thing that does is they look, it's just like microservices, the concept is just like an assembly line. On an assembly line, we don't care about what happens before and what happens after. We just care about whatever is passing through my bus. I pick it up, it's for me, I do something, put it back, and it continues. That's the concept of a microservice. It is specialized, loosely coupled. So if we go to a comparison between our monolithic applications and microservices, even when we're doing SOA, what we have is this. We have monolithic application, basically put all functionality. So for example, this is the ordering service. This is the, for example, the billing service. This is all different services. It's an application. Everything's together, right? There is tight coupling. They're running in the same container. They're running in the same IaaS, in the same application. This is a monolith. And then how do we scale? We basically get lots of instances of the same thing. But they need to go together because they are interdependent. What microservices says is I need to design those things in a way that each element, I put each functionality, focused, special functionality, into its separate service, separate container. And they actually run, and then we can define if they run on independent containers or in the same container. But they run in independent processes. Which means that if this fails, doesn't matter. The solution still continues. Because not the whole solution died, only that. If I need to scale, I now need 5 of the billing, 4 of the ordering, I can do that. Because they are independent, completely independent. That's the power of the microservices, is creating complete decoupling, focused information. Another example is in a monolithic application, we normally have, imagine that you have here multiple tables that you need to interact with. You have the orders tables, you have the billing tables, and so on and so forth. And you have UI, application layer, and yes, you have APIs here, and then you have SOA and everything. And then you have here the data layer, and then it goes into a big thing that needs to be transactional and so on. In the microservices world, each of the service is responsible for talking to their own data store. So if I go and do CQRS, the command is, for example, talking with a SQL database. Why? Because I'm storing something into SQL. The querying might actually be a storage account. Because my projection is generating a JSON file to respond. Because I'm going to use Angular or Knockout or something in order to bind that JSON into my UI. So in microservices, each of the services can have their own data stores, and they are independent. We go for a decentralized store. The only thing that is the single source of truth is what? The message bus. And the way we actually keep reliability and we can maintain that it's repeatable is because we're doing event sourcing. Now we're starting connecting the dots. So microservice is about componentization, so the ability for me to replace parts. It's so small, so nimble, they are independent that I can actually replace. So for example, today one of the issues is, and big companies have an issue, which is, I have a product. The binary for that thing, I work in a company that has, like a binary has 1.3 gigs, just the binary. It's pretty big for me to go and say, oh, there's a new technology. Yay, let's adopt it. Let's stop this development and do a new one in this technology just because it's cool. It doesn't allow you a lot of agility in the process. With microservices, because I have small functionalities, I can actually slowly start replacing because they are all independent. I can go and say, oh, now I have a system which is a microservice which is grabbing a type of message, like the ordering event from the queue. Now I create a new one and put it there also, side by side. And now I have two versions running side by side. And they are running. And I didn't have to interact with anything else in the system. I just placed another thing looking at the stream of events, right? And then I can take the other one off whenever I want. So what I did was create components, individual components, which allow me to also be more agile. Because now I can deliver more, I can be more agile and adopt new technologies without breaking the thing. Why? Because it's small parts, I can actually go without breaking the full house. Another one is organization around business capabilities instead of technology. One of the things, and this is here, one of the things we normally do is we organize based on the layers they are in. This is the UX layer. This is the application layer. This is the integration layer. This is the data layer. This is whatever layer. Security. This is whatever. That's all amazing. It's all amazing. There is only one problem is when you actually go and start developing these things, and you have, for example, a lot of different Scrum teams. One is developing something on the cross-cutting security layer. The other one is building the data layer. The other one is building service layer. The requirements for them in terms of integration are massive. If one fails, everybody fails. With this, you basically go and organize around business capabilities. And you say, it's around the ordering. I have a microservices for ordering. Everything of the ordering is there. I have a microservices for billing. Everything's in there. From security for, authentication, authorization, all those elements, it's all there. So that team needs to think about all the different parts. Create independent microservices, but they need to think about and be organized as business capabilities rather than technologies or layers they are working on. So this means that now, when I want to put billing v2, I can actually put billing v2 because I'm not dependent on security v1 and data tier v1.3 and something like that, right? So this creates that capability. Smart endpoints, dumb pipes. So one of the things is, remember Enterprise Service Bus. How many of you have an Enterprise Service Bus like BizTalk or TIPCOs or WSO2, things like that? It's really good. It's about integrating different applications. It's really good for what it does. The problem is, in most organizations, the way it's been implemented, you should try one thing. You ask someone, is this system really reliable? They say, yeah, everything's reliable. So, if I take this plug off, your whole business won't stop. I actually pulled that stunt in a telco. I was with the CEO, and he told, no, this is rock solid. everything can fail and our business never goes down. I have been doing an assessment for a couple of weeks there, and they had a lot of BizTalk. It was everything was going through BizTalk. Yes, you can do a lot of high availability with BizTalk and things like that. So went in and said, okay, so you're saying that if I randomly choose one cable, and we were in the data center room, if I randomly choose one of these cables, your business is not going down. Do we have a bet? And it's like, yeah, of course we have. So I can randomly pick one up. Yeah. Okay, so I reached out, just did this, took one of the cables off. And his phone immediately started ringing because the data, all the system was down, everything. Because I knew which one was a BizTalk. Put it in, everything is working in. Take it off, everything breaks. ESVs are really good, but also create the single point of failure. Because everything now needs to go through them. They are the big orchestrator of everything, so if they fail, nobody knows what the hell to do. So what microservices say is, I need to put this on a queue. Every single service has the knowledge of what type of message is it going for, and he will do his small little work and put a new message there. And so I don't have a single point of failure. I can have small elements that fail. And if they fail, we'll then recover, but not the whole business will fail. Okay? So this is the NumPy. It's designed for failure. That's one of the parts. Decentralized data management, we saw here. Every single one of them uses its own data. And infrastructure automation. This actually allows, and it makes it very easy to do automation. So one of the things, microservices come with a very interesting newborn thing, which is containers, containerized. Have you heard about application containers and things like that, like Docker, Rocket, Cloud Foundry has Warren, for example. Microsoft, even worker roles can be leveraged as a small container. So this, a container in that respect is where we are going to put our services working. So, and in types of microservice, we need to understand an app means something different. An app is a combination of services. It's not an end user app. That's a different thing. In a microservices world, an app is composed by multiple different services, which together actually do an end result. They are together, but they are not dependent on each other. Okay? So for example, the billing part, I do an order. Of course I'm going to have a billing, but does the billing know what the order does? Has no clue. So someone goes, puts a message in the queue, the order microservice picks it up, the order goes and validates something, that's the first stage, puts again into the queue, another part of microservice for the order, which is the one that actually goes and puts that into the ordering system. It goes there, puts a new message to the queue, then it said order done. Immediately the billing service picks up the order done message, does whatever it needs, integrates with their payment system, and continues on. If something happens, oh, we didn't do, the order failed, the validation didn't work, it wasn't there, doesn't matter. I still continue my process. Okay? So it's very independent, and I can do continuous delivery without breaking the damn thing, which is the hard part. Questions? Microservices? No? Is this getting helpful or not? So, real-life implementation. This is a real-life architecture of CQRS. This was made for a tablet. So there was a company that has its own tablet, its own Android device tablet. One of the issues is you get from Android, from Google, you get the OS. You don't get the services like the over-the-air updates, like the application updates, like the crash dumps, like all of those things. You don't have services. Here's the OS. Now deal with it. So you need to build all of this. So we actually had to create all of those things, all those services together. And we were not targeting like 100 devices. It's like 5 million devices in the first wave. So what we did is, okay, let's put this on a secure OS. So that's commanding. You have a service API. So a service API, for example, firmware has insert, as post, put, delete, and it has a get. That's a query. So put, post, delete comes to here. What this service client does, the only thing is transforms the RESTful call into a message. Just takes the message, takes the request, generates a message, and puts it on the event bus. The only thing. Then this message, which is now, for example, insert firmware command, is going to get taken by the insert firmware command handler. It only knows that eventually there will be insert firmware commands there. You will pick every single one of them. I can scale up and down that thing, just that specific. So if there is a surge in the number of requests or the number of something, I can only up and down, scale up and down that specific command. So I can actually have that, that independence. So then every command handler drops an event. Events like, I started doing this, I ended doing this. So this is the life cycle event. Then it sends also execution event, like firmware inserted, firmware updated. So it's an execution. It's saying I finished what I was supposed to do. The other two is to get a timeline in between. Then everything is being done using event sourcing. We're storing every single event that comes up. We're storing it in the right order. So at any given point in time, I can replay, I can have audit, I can have whatever I need. Then when this guy says firmware inserted, this guy immediately, my projection or denormalizer, picks it up. The same way like this guy is storing it, this guy is also pick it up. And it's actually go to the access layer and what just happened? Goes into the data layer and checks what is there, and then generates a JSON file. In more detail, this was the actual architecture. So I have my RESTful API. Everything that is post, put, delete goes to the service client, which drops a message into event bus. This in Azure, the best probably would be event hubs. The reason is it's massively scalable, and you can actually hook other systems like complex event processing, the analytics. So for example, streaming analytics, which is interesting because you have, in event-driven, you have 3 types of event processing. Simple event processing, stream event processing, complex event processing. Simple is your bus only has one type of events, which is a notable event. In stream, which is this case, I have actually multiple types of events going, but some only for one command handler, only one of them is notable. It's a notable event, nothing else. Then we have the other one, which is a complex event processing. That complex event processing is when I have multiple types of events and I'm finding patterns inside. That's complex event processing or streaming. So what happens is, and we can go into the flow, imagine I'm going to insert a specific firmware. So I go to my UI, which was on a website. This website was sending into was calling a web API, because we wanted to have web API, we needed to control that. Calling a web API with a post, saying, oh, go and insert this thing. This service client, as soon as I call this service client is just a pass-through. It's just a library that basically understands how to create the message based on the request that got. Okay, so it knows how to transform a web request into a message. Nothing else. Very dumb. Every single part. One of the benefits in this is the complexity level is very, very low when you're developing this thing, because you're only focusing on one of these elements. So you go in, you insert, this guy goes to service client and says, hey, here's insert firmware command. Here it is. Now there's a message here. Now this is a reliable queuing. This was Event Hubs. It's reliable. I get this stored in the right order. Everything's well. I'm here. Everything can burn down. Doesn't matter. I did never lose it because it's reliable. Now my command handler, I have a command handler, which is my insert, where's the name? It's insert firmware command. This is the handler, this insert firmware command handler. The only thing he thinks about is doing one very significant thing, which is go and find if there is an insert firmware command message there, you will pick it up and go through, and basically was doing validating an APK, validating the MD5, and validating the group, and then inserting that into the database. And so basically this would go pick up the message, do that thing, and send events. Events like throughout the process, one of the things, remember I spoke about being able to remember insights, trackability of the system. So as this guy starts, we actually have events, lifecycle, execution, operational, and business. So lifecycle, insert firmware started, insert firmware ended. I know exactly, at any given point in time, I can tell you how much time did that process take. This will allow me to understand what's the average time that it takes and immediately identify if there is a problem, a brownout or something strange in that process. So I can create like a range and say, no, this normally takes in between like 50 and 150 milliseconds. More than that, I need to look it up because something is probably going wrong. Then I have a couple of execution events. So small execution events like APK, firmware APK validated. It's an execution event. I executed this step. Why is this step important? Because if in the middle of the operation the command handler fails, you will go back and the message is here again because it's reliable messaging, right? The first thing it picks up, it goes and says, okay, tell me what was the last event, execution event you received. Oh, it was this APK, so I don't need to do it again. I continue from there on. So I don't repeat whatever I have, which is a common mistake. So those are the execution events, and then I have a main execution event, which is insert firmware. I can't remember how we call that thing. Insert firmware done. Then we have operational events. Operational events are normally events that whenever you interact with third-party systems, in this case storage. So what happened is we get the request saying, hey, here's the APK and insert it. what we would do is we would insert the APK into storage account and the message into the queue, because it's too big in order to put in the message. So what we need is, in order for me to validate the APK, I need to go where? I need to go to the storage account. I need to connect. So the operational events is tracking how much time it took to connect, how many times it failed, how much time it took overall in order to retrieve that information. This is the operational events is what's going to allow me to say if there is a brownout, and actually prove to Microsoft if there was a brownout. And yes, you need to prove that one. An outage is easy. If it's a system-wide outage, is easy. Even if it's not, we have New Relics and things like that. If it's an intermittent thing that actually only affects you, it's painful. It's painful. This was the only thing, the only reason why we placed this, and the only reason why we actually, in most of the times, when we said there wasn't, you actually broke your SLA. Oh, but this was on. Yes, it was on, but you didn't go with your scalability targets. So you actually broke it. Oh, what the information that you have? Here it is. I have the full audit trail of that. And the good part is we actually get our money back, which is the financial back to SLA. So it has a lot of benefits. It starts, the first time you get into it, it's a little bit difficult, but then it's pretty simple. So this went and goes, the command line to pick it up, then the event handlers receive. So the events are only, so for example, the events, imagine that the same way as when I'm doing a web application or a Windows Phone application, I have a button, I have click, double click, I have a bunch of different events. Not all of them are subscribed. I don't need to subscribe them all, right? It doesn't mean that they are not raised in the first place. Just means that I'm not subscribing them. The same thing here. Most of the events, a large part of the events, I was not subscribing them. I could. That allowed me the ability to, if I want, I could change and say, go into troubleshooting mode in the configuration, and I suddenly started to actually track all of them and go into detail. And for example, the event handler would pick a certain event and send the information, the complete stack and everything, to some logging system for me to take a look at. But in the normal terms, I don't want that, because that gets a lot more power that we want to put in it. And this was the commanding part. Any questions there? No? Then we have the querying part. That command part, remember, I did all the command things. I placed into the database, but it looked normal, a normal solution. So I go, do some processing, put it there, just wrapped in a different paper. Here is where the difference lies. I now get, as soon as my firmware, so it picks it up in main event, which was the firmware, insert firmware done. As soon as it goes, this projection actually knew exactly what type of projections. Where did firmware actually was needed. So I have one projection per each view that I want to take. So, and basically what we would do is we'll take that. We already have a JSON file. If the JSON file existed, I'll just add something to that JSON response. If it doesn't exist, I would create the JSON response. And basically that would be stored in the storage account. And then we could put caching on HTTP headers. I can use the cache headers in HTTP. So now when the device calls and does a get, the only thing this system does is go to the query service, and the query service gets it, the JSON response. Doesn't do anything, doesn't think, doesn't do anything. The only thing is grab from the view store, and give it to you. Nothing. It's a JSON file. It's already ready. We were using Knockout.js here in order to bind the information. It was the actual response. It didn't even need to, translate this list into response. It was the actual response. If you go into this view store, you'll have all the JSONs for people. So like products, you have firmware list, you have the JSONs. You have like application update, you have the list. The response were there. There was no response there that you could see here that was not already pre-made. Yes, there is a trade-off, but that trade-off is very simple. If I want, I don't need that much real time, I scale down this and I basically save money. I need more real time, I scale this up. And they actually come up all in near real time. The best we could do was 1 millisecond, so it was pretty close to real time. So this way, and then all the processes of getting even the lists for the application. What we did and what we got in the end was the same system did exactly the same thing for the customer, exactly the same thing. What were the things we learned here? Is by doing this, we had more control. So instead of having a method that had like 300, 400 lines of code and a bunch of things, and it took like a day, 2 days in order for someone to develop something, now a single command handler, microservice, have max about between 10 to 20 lines of code. And that's it. And it was simple. And we actually created a template that was a microservices template, a command handler template, which is the first thing it would do is pick up a message from the queue. The last thing is put up a message in the queue again. So complete that one, mark that one as done, and put the new one. That's it. And so in the middle, it was a couple lines of code. Very simple. So also, that meant it was very easy to test the capability of the system. Is it working? Because it was very independent. And then we could have the integration going through. Also, we found out that this, apart from scaling a lot better, because we could actually scale independently, so we found that at some point there were days that we actually predicted the spikes. We actually could just increase, but it was not the spikes for the old UI stuff. It was only the spikes for the get queries. Because apparently in Christmas, people like to give away tablets. And the first thing you do when you receive a tablet on Christmas is open it up and connect it. Newsflash, you need to update the firmware. So of course, we'll have like 500,000 or 1 million connected and saying, give me the firmware. And there was no way a service would not choke. And so the first attempt that we got in here, we didn't put any, we just did this, we didn't play around with HTTP cache headers. And we went from, we had about 1,000 instances before, we went to around 100 instances. So it was a very good one, at least money-wise, because we were spending about 2 million. We went significantly down. But we were not happy, because that didn't have redundancy. So that means, yeah, the 2 million didn't have redundancy. So if I wanted HA, I would go for the 4 million. That was the part we didn't enjoy. So we went here and we went to 1/10, basically, almost 1/10 of the price. It's like, oh, this is good. We can do better. Each time the get comes in, the get is always the same. It's a firmware. I have this version, give me the firmware. So what do? We actually played around with HTTP cache headers here, and we actually played around with HTTP cache here at this level. So actually, we said in 10 seconds, if I put a new firmware and you don't see it in the next 10 seconds, is that in any harm going to get in the world? No. We asked the product owner, and the product owner said, 10 seconds? Put it like 5 minutes and it's good enough. And we said, okay. We placed that as our cache header. So now, a system for about the number that is supporting now is about 5 million devices, live devices, is being supported with 4 instances. 4 instances. It has one web service, one website. It has, we created the same worker role has a bunch of commands, but actually each command runs in their own application app domain. So they are in their own processing app domain. Unfortunately, there was no good container for .NET. Now we're getting it. Docker is starting to get also into the .NET world. So they were completely decoupled. I could spin up and down. And I had 2 more. So from the 4, we decided to put 6 in order to have redundancy. And this started to cost us around 100,000 with redundancy instead of the 2 million that we started without redundancy. So when we talked about designing for the cloud and thinking about also sustainability and microservices and CQRS, and that is the power. The power actually now, and we actually joke with them saying, since we saved you all that money, can you get like a part of that for us? I can give you my bank account number. That didn't work too well. But this is the type of thing that will make, one, the teams are now very simple. They are independent. They don't wait for each other. Very easy to mock. Very simple kind of coding. Very simple to implement coding patterns and validation. At the end, you have one thing. You have a solution which is reliable and is quality and enables you to grow. That was the biggest lessons we learn is now with this pattern, we actually have something that is designed for the cloud. More than that, is designed for as a multi-tenant distributed system. Because in here, we actually use, have you tried API Manager? Azure API Management? It's really good. We actually, at some point, we decided because of this and because of the data we were getting, we actually placed an API management, an enterprise API management service, which would mock, basically would sit on top of this. And I can then change the versions, change the signatures in the back end, but the front end I could basically do based on routing. I can actually create it like subscriptions for this service. I can actually now in the latest service, just before I left, the license system, we were able to go and support other companies like this one that was creating their own services, their own Android tablets. They could just hire this as, I don't know, Android OS tablet as a service. So they can just hook it up and it was done. And this started to be a complete revenue stream for the company, even more than only supporting their systems. And so we needed to create like throttling. There are companies that now have the standard version, which allows them to have like 100 or 500 devices connecting per hour. And then, so all those throttling, all those rules and everything, it's what the API management does. So that's what we use here. So this is just an example of what you can do when you actually think about designing for the cloud, the real thing. It's not the clouds that everybody talks and nobody or very few actually agree on what it is. It's about designing for multi-tenant massively distributed systems running on an abstraction of commodity hardware at internet scale, which is composed by multiple services. That's a real cloud application. And in this microservices world, an application is no more than a combination in small parts. So this is very small services. This is an application. It's a combination of small services. Questions? One at a time. Was that helpful?
Yeah.
Yeah? No questions? Either you fell asleep or something. So if you would like to know a little bit more, you can email me or tweet or whatever. Feel free. I'm not in the services business anymore, but I'm still active in the community and doing these things now in a massive scale, because now it's not about only I'm doing this for customer A, B, or C. I'm actually doing something on massive number scale with healthcare. So it's an interesting world, and we're actually starting to implement some of this in our biggest products, flagship products. And so if you need any help, just feel free to reach out. Okay, thank you very much. Hope you have a great rest of event.